imprevisível para o Instituto. Vamos começar. I was saying that the audience is always unpredictable in the Institute, but we shall begin. Perhaps people will come in late.
It certainly happened before.
They never understand what's going on because the argument will be halfway.
Sorry, Monday morning and Friday afternoon is a little more predictable.
Yeah.
You have to.
We should beat these people up. Então, o professor John Collier é professor visitante do laboratório de ensino filosofia e história da biologia. Ele é o terceiro ano que ele vem aqui trabalhar com a gente, com a bolsa pesquisador visitante especial do CNPq. Infelizmente o projeto está acabando, então em julho o projeto termina, mas eu espero que o John continue nos visitando depois por outras vias. E aí eu propus ele uma fala sobre função ecológica, que é um tema que ele está trabalhando no momento, a gente está trabalhando junto, e também é uma oportunidade para a gente colocar em teste algumas ideias que a gente está discutindo. I just explained to our visiting researcher here, and the idea of the talk about ecological functions, a good idea to put the arguments on trial again.
Right.
Great, John. Thanks.
Okay. Thank you. Sorry, after several times here, I still don't know very much Portuguese. I find it a difficult language compared to, I know French and a bit of Spanish, and German. In any case, I'm going to be talking about ecosystem function. And when we talk about function is for something. It's always for something. So one of the first problems that needs to be dealt with is what is it that the ecosystem function is for. Obviously it's for the ecosystem, but how do we need an account of function that will allow that. And then we need some criteria for what makes an ecosystem an ecosystem. So we know how the function contributes to the ecosystem identity, essentially. Then there are issues about ecosystem complexity and its consequences. It turns out that Bob Ulanowitz, who was here a couple of years ago, has a wonderful way of dealing with this issue that I think works really well. So I'll be explaining that. And then finally we want some criteria for ecosystem resilience, because that seems to be the goal of ecosystem function. Ecosystem function should support the resilience of an ecosystem, make it better in sense of more healthy, more stable, it's flourishing, basically maintaining its identity. And that helps to define what function does, so we can identify ecosystem functions. Now, I'm not going to talk a great deal about ecosystem functions in particular here. I'll give a few examples, but I don't have time to give very many. First of all, there are two senses of ecosystem function. Most of the literature is aimed at the interaction between humans and ecosystems, or human society and ecosystems, where the ecosystems are seen as being something outside of human society, or human society being outside of the ecosystems. And this has increasingly been challenged recently by various authors, including a co-author of mine who I wrote a couple of papers on ecosystem identity with. But it's more general. But much of the work that we see on ecosystem function deals more with the function for humans from an anthropocentric point of view. What's often called socio-ecological systems. And they're often thought of as being the social system and then the ecological system, and then some sort of combination of the two that is often just a linear combination without any clear attempt to integrate the roles and put humans into the ecosystem. I'm not going to be particularly concerned with that. There's another notion, a non-anthropocentric one, for the function that an ecosystem might provide for other species from other ecosystems, like migrating birds, for example. Migrating birds could be considered to be part of the ecosystem, but they're usually temporary and visiting. Sometimes they contribute a lot, in which case they may perform an ecosystem function. In other cases, they don't really. So that's why I've classified this as external. Internal, we're talking about functions for the sake of the ecosystem itself, and that's going to be my main focus. And I would argue, I would hope, that this approach in general will give a way to help integrate other species and humans in particular into a combined socio-ecological system, which is unified. But I don't try to do that here. I think it's going to be an amazingly complicated thing to do. I have a PhD student right now who is working on an egalitarian approach to biological value, and where individual species have value because of their teleology, their entelechy, if you want to call it that. The fact that they have a function for themselves belongs to them, just like humans do. So we can put humans into the same sort of comparison class as other animals, other species in general in ecosystems. I think eventually that sort of approach, which has been associated to some extent with deep ecology, is the way to go. But so far it's very underdeveloped. Why ecosystem identity matters? Well, the internal account requires that something functions for the sake of something else. So we talked about the heart serving to pump blood, which provides nourishment to the cells, so the cells in the body can survive, and the body can survive. So we need to identify that something else. So we need to give identity conditions for ecosystems. This turns out to be non-trivial. Ecosystems are often nested. So a nested ecosystem might serve a function for an ecosystem in which it's nested. So you could have smaller ecosystems within a larger ecosystem, and that smaller ecosystem, more than just providing services for the larger ecosystem, like basic things like clean air and water, it provides more complex functions than that. In fact, I would say that's typical. And it works the other way as well. A larger ecosystem can provide functions for smaller ecosystems to help to maintain them. I haven't paid too much attention to the other direction, but I think it follows pretty much the same rules, so I didn't single it out as a special case, but it's certainly possible. And I would say that this overall approach is the best account of anthropocentric functions of ecosystems because it forces a more holistic view. That would include humans and human society into the ecosystem. Okay, there are some problems that are well known with defining ecosystem identity. They're not superorganisms. They're not fully self-maintaining in particular, and they're not strongly adaptive in the sense of being selected for their adaptive capacity. So there's very little external control on their adaptive capacity. It's all internal. And this is quite different from autonomous members of species where they have a history of selection, which has picked out those characteristics that are most functional. Also, boundaries aren't well defined. So they're not autonomous. But autonomy does come in degrees. It can be stronger or weaker. So even though it's not enough to call it autonomous, there's some degree of autonomy, I think, going on here. And I'm going to make use of that in giving a notion of what it is to contribute to ecosystem identity. It'll turn out that ecosystem identity is closely related to notions of resilience once we bring in work by Bob Lanowitz. This is probably not surprising, but it's not straightforward or easy either. Another problem is boundaries aren't well defined, unlike for organisms. For example, this came from a talk I gave a few years ago in France. The Chesapeake Bay watershed is not necessarily the boundary of the Chesapeake Bay ecosystem, although for some, in some cases, the watershed of a given stream is in fact the ecosystem of that stream. And there are cases in the edge of the Rocky Mountains where there are different ecosystems for each stream that comes down the mountains. It may be true in the Chapada Diamantina where I was recently, but unfortunately I didn't get enough chance to see the different areas. There I noticed there's a difference in differences in altitude make a big difference in the ecosystems that you find. And there's a somewhat continuous range from one to the other, so the boundaries aren't clear. But given that ecosystem identity depends on what holds it together, what holds it together comes in degrees. That's to be expected to some extent. Embedded ecosystems can go some way to resolving the boundary problem. So we can talk about the overall ecosystem of the Chapada Diamantina, for example, and then talk about various embedded ecosystems within that overall ecosystem. Parts of ecosystems, species and interactions, the two parts that are important, can be interchanged while maintaining ecosystem identity. But we don't get this sort of substitution above the cellular level in organisms. So that's something that needs to be taken into consideration when we're considering ecosystem identity. Ecosystem identity certainly just isn't made up of the species within an ecosystem, although some people try to define it that way. Okay, in general, in dynamical systems, which ecosystems are, parts will be more closely integrated through energy and matter flows in some cases and others. And there will be other factors as well contributing to system organization. But the difference in the way the parts are integrated is going to be especially important. There will be overall considerations as well. And I'm going to separate the two out to some extent and show how they're related using Lanowitz's method. I propose that if there's an overall balance of integration within one set of parts than with another, then we can call that integrated part ecosystem cohesion or system cohesion. So the cohesion basically is dynamical forces that hold something together. And it's never complete. It comes in degrees. Some things are more strongly held together than others. So there will be borderline cases of cohesion. So what we want to do is we want to identify what the properties are that produce cohesion in ecosystems. And we have this idea in the back of our minds that it's going to be related to resilience, because we know resilience is important to ecosystem survival. So that's something that we're going to aim for as we go along. Okay, cohesion comes in degrees, as I said, but it's also, it comes in different dimensions. And it'll be stronger or weaker in different dimensions. And we want it to be that the dimensions in which it's weak or brittle are relatively improbable, so they're not likely to happen. So with humans, for example, heart attacks are really dangerous for our survival, but fortunately they don't happen very often. So they're not a big concern. They don't affect our cohesion profile because they're relatively improbable. Well, they do affect it to some degree. Now, cohesion both unifies the system by the forces holding it together, but it also differentiates it from other systems because the forces holding it together are stronger than the forces that are pulling it apart. So if we have two systems, then each one has a center, so to speak, where the forces are pulling it together, one here and one here. And the two are separated from each other because those internal centripetal forces are stronger than forces between them that might be pulling them apart, or the forces between them in general. And this will be on average across the cohesion profile, depending on the probability of the interactions of various types. So some important characteristics of cohesion I've already suggested. It's the closure of the causal process that individuates something by the centripetal or inward forces. Centripetal is Bob Ulanovic's term. Cohesion comes in degrees. Cohesion is multidimensional. A cohesion profile is made up of a strength divided by probabilities. So a weak dimension is not a problem if disruptions are unlikely in that dimension, like the heart attack case. For organized systems, the structure of boundary conditions on matter and energy flows are more important than the flows themselves. So information is the most useful measure. So when we're talking about the cohesion of an ecosystem, for example, we're interested in in defining the boundaries, the extent of the ecosystem. Then the nature of the boundary conditions and their probabilities will become the most important. And we can put this into a nice linear form using the standard format for information, the sum of the probability times the log of the probability over the various factors that are involved. In this case, I'm talking about boundaries. It turns out that it's useful we're talking about internal relations as well. So the cohesion profile is related to the strength per information unit. High information contributes to stability, but it can't be too high or else we lose flexibility. Too much information can make a system brittle, which actually reduces the information in the sense of the previous point of this summation. So for ecosystem cohesion in particular, by looking at analogy to organisms, organizational closure is a suitable criteria for identity in organisms. That part of the closure that contributes to survival and reproduction, like I've called autonomy, following Kant. Contributions to are functional, giving a clear criteria for an organismic function. But ecosystems aren't autonomous, as I've said before. But we can still use the cohesion concept in its form of organizational closure. Because even though there won't be the sort of strong closure you get with organisms, there'll still be some degree of closure. And as long as the degree of closure is enough to distinguish it from other ecosystems, because the forces pulling inwards are stronger than the forces that are moving outwards, then we're okay. That's all we need. So ecosystem closure, like autonomy, can be partially open, but it must be dominantly closed. That's its major characteristic, will be closure. Typically, ecosystems are described in terms of a network of flows of one or more types. This goes back, we're quite a long way now in the ecological literature. These flows aren't rigid, but have certain probabilities. These probabilities can be rendered conveniently into an additive form by converting them to information measures. And it's the same equation here, except now we're talking about the probability of the flows between the the individual units of the ecosystem, or the nodes of the ecosystem network, not the probabilities of boundary conditions. Combining the two together into a more coordinated measure would be a nice thing to do, but I haven't actually done that yet. It's something I really should do, or find a tame mathematician to do for me. Anyway, this implies that too much information or too little can disrupt organization. Well, the reason is, if we have information going upwards, if we have very low information, well, information is zero, then we're obviously going to have zero organization. And as we increase the amount of information, we still get, if the information is low, we still get quite low organization. The interesting thing is at the other end, here we have very high information, the probability becomes close to 1. But if the probability is close to 1, then the log of the probability is going to be 0. And that means the organization is going to be low, because everything is regulated into a nice orderly pattern that's highly redundant. So if we're going to look for organization, we're going to find it in this middle area. That's not too ordered and not too disordered. It's going to have a little bit of both. So I've investigated to some extent the notion of ecosystem depth. Because depth has been used as a way of talking about organization mathematically and also physically. And so we're dealing here with something that's mathematically related to organization and has certain consequences as a result. But also intuitively, the notion of a deep ecosystem is a better one, a healthier one, a more resilient one. So a highly organized ecosystem is going to be in general better. It turns out there are some caveats about that, which when I get more specific about the nature of ecosystem organization and how to measure it using Eli-Limitz's method, I'll mention these caveats. We can measure organization in terms of the computation required from its simplest or most condensed description to get its surface structure. This is due to Charles Bennett, a mathematician who works for Bell Labs. This implies there will be redundancies at a large scale. It'll be holistic. So organization implies a certain degree of holism on this definition. But as well, there'll probably be smaller scales, which would get redundancies. And it's quite possible that these will overlap. So this notion of logical depth places limits on the sort of structures that we can call organized. And it turns out, if this is right, if the surface structure is very shallow, then there'll be little organization. But that means it'll be more or less random. Or else it'll be so highly ordered that there's only one possibility. So it makes sense that an organization will require a fair amount of computation to work out from its the basic principles that describe it, essentially, to its actual structure. Alternatively, we could measure the thermodynamic depth, and that tells us the amount of work required to produce the organization. And again, this gives us some idea of what effort went into the production of the ecosystem. A more highly organized ecosystem is going to require more effort. It's actually easier to get soldiers to march together goose-stepping than it is to get them to spread out in a suitable fashion to take a city. They still have to be organized, but they have to be organized in a much more complex, interactive way in order for that to work properly. Same thing with ecosystems. Information measures are better suited to the Bennett version when I'm using information measures. But I think the thermodynamic depth notion can act as a check and control on its measure. So it's useful to keep it in mind how much work is actually being done here, how much work is required in order to get the organization available. If it turns out that our measure of depth using the Bennett measure is tells us one thing, and then we look and say, oh, but that's impossible, there just isn't enough energy in the system to produce that organization of that nature, then we have to throw, we made a mismeasure someplace, we made a mistake. We've got the basic dynamics underlying the ecosystem wrong in some way. So having more than one way of approaching ecosystem organization is highly useful. Despite that, I'm going to argue that Ulanowitz method is the best and most illuminating. What is function? In the English-speaking world, largely, the most popular kind of function for organisms is that it's a product of selection. This is called the etiological approach. But this isn't useful for ecosystems, since ecosystems are seldom in competition with each other. So it looks like function in terms of contribution to autonomy, self-producing organizational closure, is more promising. Except, as I keep saying, ecosystems aren't autonomous systems. They're not superorganisms. There are people who have investigated that and argued in its favor, but the arguments have never worked strongly enough to be able to convince people in general. So it seems like the best scientific view of ecosystems is they're not superorganisms. It'd be convenient if they were. It would make things a lot simpler in analyzing function, but they're not. So I propose that a property of an ecosystem is functional for that ecosystem if it contributes to the cohesion of the ecosystem and so to its individuation. And cohesion is what's necessary for the organization of the ecosystem. In fact, I can go further than that and say that the cohesion of the ecosystem is just its organization that contributes to its self-sustaining character, to the degree that it's self-sustaining. That's not all the organization. There'll be lots of organization that doesn't do that. Now again, it turns out that Ulanowitz has a convenient way to measure the difference between the two. And it turns out the difference between the two is quite important when we're considering issues of resilience. Anyway, this approach is more similar to the notion of autopoiesis, except that it's more open than autopoiesis is usually thought to be. Some examples of the ecosystem function, just so, you know, this is just a check on, are we really talking about something that makes sense here? Worms break down soil and aid the propagation of plants, which in turn provide food for herbivores and eventually carnivores. And carnivores in turn keep the number of herbivores in check, reducing the likelihood of overgrazing and ecosystem collapse. Especially the herbivores tend to help to fertilize the ecosystem. The soil bacteria also play a role here, and they aid the fixation of nitrogen, aiding or even making possible the growth of their associated plants, and aiding the cycle mentioned above. Another thing I could maybe mention is the role of fungi of various sorts in providing nutrients for plants. It turns out they're very important. Bison eat grasses while grazing, break up the surface layer, allowing grasses to propagate more easily. They also provide fertilizers and remove woody plants and weeds that might otherwise invade the prairie. It's thought that mammoths did the same thing in the high Arctic. And when mammoths disappeared, then we got an invasion of this nasty little bushy stuff that covers the ground and tends to keep other types of plants from coming in. So you get a less complex ecosystem as a result. One that's more subject to wildfires in particular. What's important here, I think, is that each of these functions, they have a cyclic nature. The closure is an important characteristic. These closure puts constraints on the way the ecosystem can act. But furthermore, they interact with each other in a circular way in many cases. So you get circles within circles. Alan says ecology is about a bunch of bagels. You can think of the circles that go around, and circles that go around, and they're combined together into a torus. It's an amusing analogy. Okay, ecosystem functions, roles, and services. I think this is a distinction that's fairly useful. Not everything in an ecosystem is functional, only those aspects that contribute to its cohesion and thus to its resistance. Ecosystem role is not the same as ecosystem function. Invasive species, for example, can have an adverse role in an ecosystem. So we can. It's quite common to think in terms of mechanisms and think, okay, there's various mechanisms, processes that are occurring in the ecosystem, and the identity of the ecosystem is just the sum of these processes. But some of these processes are adverse. They work against ecosystem stability, ecosystem resilience. So they're not part of the ecosystem identity. Regulation of services, however, certain general needs such as water, sunlight, and soil are not functions themselves, I don't think. I call them ecosystem services, not the services the ecosystem provides outwards, although certainly that would be one aspect of this sort of thing. Clean water to other ecosystems. One ecosystem can provide services in this sense for another. The regulation of services sometimes is functional. For example, in the Amazon rainforest, the processes involved in the formation of clouds, water evaporating from the ground. There's a circular process going on here that leads to heavy rainfall. Heavier rainfall, if the rainforest is cut down, then the rainfall decreases. In fact, you can get a rainforest turning into a desert if you cut down the trees. So this is a case where we do have something that's related to a service normally, but also there's a functional role in maintaining that service within the ecosystem. So the two ideas aren't entirely separate, but I still think there's a certain value in keeping the ideas separate. Because normally services don't contribute to the survival except in a very general way. So they're not part of the organization per se. It's useful to look next at some aspects of ecosystem complexity. Organizational cohesion, being typically cyclic, allows highly nonlinear positive and negative feedbacks. And these are going to have to interact with each other. If we have just negative feedbacks, then things will be damped down until they don't exist anymore. And if they're positive feedbacks, we can get things growing so much that they are doomed to collapse. So there's going to be an interplay between positive and negative feedbacks within a typical ecosystem. This implies that we're going to have nonlinear equations describing these. And that implies that we can't reduce these processes to underlying physical processes. So an ecosystem organization is typically going to be a non-reducible characteristic in and of itself. We can't just add together the contributions of the parts and expect to get an ecosystem. This means there'd be no single ecosystem model that captures its cohesion, let alone its whole structure. And this has been argued, I think, very convincingly by Robert Rosen and by Alan. We need to use multiple ecosystem models. And Graham Cumming and I, who wrote about ecosystem identity, argued for a multi-model notion of ecosystem identity. There's no single notion of ecosystem identity which will apply in all cases. Physical factors matter, species matter, interactions matter, the flow of various nutrients matter, a whole bunch of things matter, but if we try to take each of those as being what really matters to the identity of the ecosystem, we'll find that we fail, basically. So we got complaints from people who refereed our paper that, well, I've been using a physical notion of ecosystem for my whole life and it works perfectly well. Well, yes, it's self-confirming. And you're going to take cases where it works better than in other cases, but it doesn't mean it works in every case. So despite those objections, our paper got published. So the complex organization implies nonlinear responses to interventions. This is sometimes called the principle of unintended consequences, which make ecosystem management a tricky business. So what we'd like, other than preserving biodiversity and habitat already there, which are the two methods used most often right now to try to save ecosystems, are holistic criteria for ecosystem resilience. And as I argued before, we have to include the human social system within that in order to get a true understanding of what the resilience of an ecosystem is. And that, of course, gets complicated because it involves politics and money and all kinds of things like that. So, moving on. There have been several properties proposed to underlie individuation in ecosystems. And stability, it's a very general property. And clearly it's important. Ecosystem health is too vague. Has much the same problem as stability. Both can, if they're taken too seriously, compromise the possibility of the ecosystem for growth and development, which is an important aspect of ecosystem resilience, that they have capacity for growing and changing as they mature. This is well recognized. So if we try to manage an ecosystem by making it just concentrating on stability, you want to keep it exactly the way it was, then that's actually going to be risky to the overall resilience of the ecosystem. Although often that's what people want to do when they try to manage ecosystems. And there's a lot of political pressure to do that. They want, they want things to be just like it was when they were children and saw it and were impressed. Resilience is a widely used concept. It reflects the capacity of the ecosystem to resist perturbations. And so it's related to stability in ecosystem health. Early definitions came from Bud Holling. The time required for an ecosystem to return to an equilibrium or steady state following a perturbation, which is also defined as stability by some authors. This definition of resilience is used in other fields such as physics and engineering, and it was called engineering resilience by Holling as a result. But it's only one aspect of resilience from Holling's point of view. It's one that is basically not especially time dependent. It doesn't change over time. And as I said, that trying to preserve that can actually make this ecosystem weaker. It's an unnatural condition. The other criteria for resilience, the other sort of resilience, is capacity of a system to absorb disturbance and reorganize while undergoing change so as to still retain essentially the same function, structure, identity, and feedbacks. So basically the organization of the ecosystem can change, but the identity of the organization never changes. There's a continuity in the identity of the organization. So what is resilience? Biodiversity is something we take very seriously right now, but I think partly that's because we're really in a situation where biodiversity is being seriously undermined in many ways due to human interactions primarily. Too much biodiversity, though, could actually choke a system out and lead to ecosystem collapse. And certain types of biodiversity, like invading species, are not typically good for an ecosystem. So biodiversity itself is not a good measure. Also, Arctic and Antarctic ecosystems have relatively low biodiversity, but at least until recently, were healthy. So we can't measure ecosystem health by biodiversity. Furthermore, there are smaller ecosystem units within larger systems. The smaller ones are typically going to be less diverse, obviously. Let's see. I'm not quite sure what I'm just going to skip this last part here, but until we get to the bottom. We'd like a general criteria from which to judge ecosystem resilience. The notions of resilience that are available in literature right now are too vague and don't work well. Ulanowitz uses ecosystem health, which is where I got the term, although I'm now using resilience because it's a more accepted term. Ulanowitz suggested that ascendancy is an important ecosystem measure. What is ascendancy? Well, it's an informational measure of ecosystem interactions. It's an extensive measure. It applies to the whole ecosystem. And it measures the development and growth as it increases of an ecosystem. And there's another important notion, overhead. It's another extensive measure, and it measures the distance between the functioning ecosystem pathways in terms of mutual information in a network with the same elements, but with random connections. Often carbon transfer or phosphorus transfer, depending on the particular ecosystem, will stand in for these types of interactions. But basically, overhead is waste processes. They're not part of the ecosystem organization. So why is it important? I'll come to that. The overhead gives a measure of the room for the ecosystem to reorganize when there are insults, perturbations to its integrity. So this is a possible measure of resilience that can be measured and predicted. Although it breaks up into several parts, I'll come to in a minute. And different parts are going to have more capacity for helping to absorb perturbations and reorganize. But if the overhead goes to zero and the system is completely organized as far as it can go, that is a bad thing. It becomes very vulnerable to perturbations. You've got a completely mature ecosystem. There's no place for it to go. And we typically end up with a catastrophe. We have the ascendancy, and we have inputs, exports, dissipations, and pathway redundancy. Well, in particular, as part of the overhead, these are all things that don't contribute directly to the organization. whereas ascendancy measures the organization. In particular, pathway redundancy, it's possible under perturbation for redundant pathways to break up and become separate from each other and become independent pathways. That's an important way in which perturbations can be absorbed. It's also true in our thinking about things in general. Most of these ideas apply to cognitive science as well as they do to ecology. Just mathematically, Ulanovitz uses a modification of MacArthur's approach to diversity of flow through a system's pathways. We have overall capacity, and then the probability of the rate of unit flow through the ith component of the system, and K is a constant. C then will be the diversity of throughputs. This is a measurement of the diversity of the system, which is likely to be related to resilience, certainly to organization. C doesn't take into consideration the network growth and development, which is a problem. Scale can be provided by setting K to T, which is the total system throughput, and we can measure that just by summing together the individual contributions to the throughput. It requires a lot of measurement, a hell of a lot of measurement, but it can be done. It's been done for the Baltic Sea, it's been done for Chesapeake Bay, it's been done for some other areas fairly successfully. We also need to include the probability of a given rate of throughput between the nodes F, I, J. So we've got node I and node J, and then we can define an equation which will sum together the contributions of the flows of the different parts. The advantage of using logarithms here rather than the probabilities of flows or the rates of flows is that we can sum them together. Magic of information is we end up with summations, where in most cases we have things that don't add together linearly. And A is just going to be the network ascendancy. And it's going to be someplace between the total diversity and MacArthur measurement and 0. And Ulanovitz basically argues that this is a measure for the actual ecosystem organization at a given time. As it increases, we get growth and development of the ecosystem. We've got local properties and global properties. These are not measures of static quantities, but of flows and possibly changing constraints. The extensive variables will be these ones, in particular the ascendancy, the total flow, the total diversity, entropy, energy flow, I've forgotten what R is, and intensively the various IJ terms. So we have a way of getting at local conditions and also measuring global conditions at the same time. They can both be measured. Stability and resilience now. What's the relationship from Ulanowitz's measures to these notions? Ulanowitz's account, an ecosystem is stable at a time if it has a high ascendancy. It is stable over time if it has both a high ascendancy and also a good overhead. And it turns out that the two can increase together, but there are costs. The overhead can be reduced by various constraints that are placed on the system, like encroaching human development is one, but there are lots of other ones. And organization increase can reduce efficiency and also introduce too much complexity, moving the system out of the safe area. So here's a diagram. we start off with a relatively small amount of diversity, relatively small amount of ascendancy. The two increase together, but then ascendancy gradually catches up with the diversity. And then we get, as Yolanda says, a reset. This reset idea is fairly well known in ecology. Bud Holling was one of the first people to make it an essential part of ecosystem cycles. So it's possible to talk about the same ecosystem with a reset here. Where the boundary is between individuation of ecosystems and resetting is arguable. I'm just going to mention that these conditions are such that it's quite possible to have self-organization occurring within the system, and consequently emergence of the system and its non-reducibility. So it has to be treated holistically. We can have emergence both at a large scale and also inside. New phenomena can emerge in the whole system, but they can also have sub-ecosystems forming. For example, the invasion of termites that form a new mound with its own microclimate would be an example of an internal emergence. We've got then ascendancy in one direction, overhead in another, and we've got a region that what's called healthy. If we go to the extremes, the system becomes either too simple or too brittle to survive. Here's Holling's curve. We have, he's talking about a case where we have, say, a forest, which is a specialty, which is being exploited by logging. And we get this figurette cycle that's well known to ecologists. What he calls creative destruction. The creative destruction isn't just anything happening resulting in the ecosystem being wiped out. It's very specific to the particular type of ecosystem and creates circumstances like supporting a forest fire that allows a regeneration of the ecosystem and return to the original part of the cycle. And Ulanowitz basically agrees with this, except that on his view of mutual information flow, he gets a diagram that's more like this. The destruction tends to be rather fast, and the period of exploitation and conservation tend to be relatively slow, so they last for a long time. The renewal period is rather quick, as you can see here. He thinks this is more accurately portrayed by the way in which mutual information actually works and contributes to growth and development. Comparison to other approaches, well, it's the time dependence is different from Holling's. It's a mathematical model, so we can make fairly precise predictions. It's a dynamical model because it can be used to test some predictions by seeing whether or not the actual changes make changes that fit the mathematics. So it's not just a phenomenological mathematics, it's a mathematics about the actual causes. Ulanowitz didn't recognize that at first in his 1986 book, but he recognized it by the 1990s. That it was actually a model of causation. In particular, a resilient system cannot have too many connections, nor too few. He calls this a window of vitality. And it turns out this is empirically about 3, someplace between 3 and 5 in actual systems that he's measured. But this is in the information log form, so it's not like just 3 connections, it's the log that gives you 3. The alternative view that's been put forward by the Santa Fe Institute is that things work best at the edge of chaos. You get the most development at the edge of chaos. And Ulanowitz says, no, that's just wrong. You're just going to get continued destruction going on. The idea is more useful for management than the vague notion of resilience, stability, and ecosystem health. It fleshes out the idea, both on the large scale and at the local scale. So here's this example of actually tested connections per node in the log form, and we see that it almost never happens to get something at the edge of chaos, which would be in this area here. We almost always get cases that are around 2, 3, maybe 5 or 6. So some consequences, last slide. Since ecosystems are typically nested, we need to satisfy resilience conditions at all levels to fully understand the system. In some cases, parts and/or processes can be substituted to either advantage or disadvantage. In growth and development, things that increase ascendancy, which it's argued tend to happen spontaneously, are the ones that will increase the health of the ecosystem. And there are reasons to think that they're more likely to survive than ones that undermine it, barring things like invasive species. Increasing ascendancy increases efficiency through substitutions. That's the reason they're more likely to survive, because they're more efficient. It also allows functional entry of new parts and processes if the system has enough overhead. If the subsystems are more or less independent, it's relatively easy to predict ascendancy changes. We just add things together. But of course they're not. So interaction conditions as well as internal conditions need to be considered, and that's much more difficult. The health of the world biosphere is the worst case of this problem because there are so many interacting parts, and it's so difficult to get accurate measurements of the interactions amongst the parts. But we can deal with smaller systems, especially areas that are preserved. They're the simplest cases to deal with. In ecosystem management, everything that contributes to cohesion is relevant. Otherwise, and even then, unintended consequences are likely in ecosystem management. For example, replacing or introducing a species with apparently similar functional consequences has led to some real management disasters. And that's partly as a consequence of not thinking holistically. So, thank you. I ran a bit longer than I had planned, but thanks for your patience.
I have some questions. If we cannot talk about ecosystems as we can talk about individuals.
The fan here is a bit noisy. Sorry.
If we cannot talk about ecosystems as we can talk about species and individuals.
Right.
Because they evolve
in such a way as to
in the
tend to
biological
preserve
sense.
functionality.
Yeah.
Right. Yeah.
Why then we just stop to talk about functionality for ecosystems and just talk about functions for species and individuals, and then we just talk about ecosystem attributes as a consequence of the low-level processes.
I think there are two reasons. One is purely scientific, which is we know that ecosystems tend to go through phases, and they're stable over periods of time, and there's a certain continuity. And we could explain that in terms of the individual components, but it turns out that the individual components aren't typically additive. We can't just add them together. So we need an extensive variable, one that applies to the whole system, or extensive variables in this case. The two most important being ascendancy and overhead. And within overhead, redundancy is important because it allows for the production of new pathways or new types of things. That this can help to explain the progression of ecosystems and why they reach a state where they have to be reset. Humans humans just die. Parts of plants die. Sometimes whole plants die. That's a similar sort of situation. We reach a certain degree of organization in our body where we become brittle, essentially. And when we're subject to heart attacks and strokes and nasty cancer, nasty things like that. And that's partly due to the system becoming too rigid, too organized. And there's a similar process going on with ecosystems. So partly it's a matter of just understanding what's going on in ecosystems. But there's another reason, and the other reason is ecosystem management, which is really becoming extremely important. There are, for a long time, when politicians would want to know sincerely what to do to manage ecosystems. I mean, not all politicians are in the pockets of big corporations, thank goodness. And a lot of big corporations actually realize they have a social responsibility. So there's a concern about management of ecosystems in order to keep them healthy. And resilience is the best notion of that anybody's come up with, but it's been so vague. So being able to specify it in terms of extensive properties that contribute to ecosystem identity might be useful for working out how to manage ecosystems in a more effective way. Right at the moment, the best thing that politicians are told is preserve biodiversity, preserve habitat, because we don't know, ecologists haven't known what else to do. I think that this is a move in a direction that may well be useful for ecosystem management. My occasional co-author, Graham Cumming, has been writing quite a bit about this recently. And it's an issue that's become more acute as things like global warming are putting more pressures on ecosystems, and just the number of human beings. Like some of the parks in Africa are becoming under risk because the park may be preserved; they have a fence around it, but the area around the park is being completely inhabited by people now, and they're cutting all the wood and burning it for fuel. And wait a second, this is not a good policy. There are better ways to provide them with heat and for cooking and for keeping warm. And really, we need to do something about that. Maybe we need to limit the human population more. There are a lot of things that need to be considered from this point of view. Because a preserved area isn't just the area that's preserved. The boundaries of ecosystems, as I've said several times here, are not well defined. And it's not at all clear that the boundary of a preserved area, as defined by some government, is going to be equal to an ecosystem. And if we only save part of an ecosystem, we're basically severing it. It's sort of like trying to save part of a body in some ways. Not quite as bad, but it's bad enough. So there are two reasons.
Yeah, okay. Yeah, management and the other.
The scientific interest, just scientific
Yeah,
interest.
but the scientific, the way that you
Yeah, just try.
it's a little bit seeing an ecosystem as an organism. Right?
Yeah, why not see it as an organism? I think the main problem is that it doesn't have the self-regulatory capacity that organisms typically have. it's a matter of degree more than anything else. I said autonomy comes in degrees. With organisms, and even with organisms, there are some difficult cases, especially amongst the fungi, where it's very difficult to distinguish one which they trade DNA. I mean, along these vesicles, it's quite remarkable. The little gates. Even with organisms, there would be difficulties with individuation, but it's much worse with ecosystems. So it's a matter of degree more than anything else. There may be self-sustaining ecosystems, but generally, when I look over the literature, the people who argue for ecosystems as being a sort of superorganism aren't very convincing, and the arguments against that are more convincing. That's all I can say at the moment. But it's a matter of degree more than anything else.
There is an argument by J. Baird Calico, which I think is a very smart argument. He says that we simply got the analogy wrong by saying that ecosystems or ecological systems are superorganisms. In fact, organisms are super ecosystems,
Yes.
which makes much more sense from a scientific point of view, because we know that organisms evolved either unicellular or multicellular from getting different things together, which were not from the same species. And also we know that our human being has a lot of diversity. We have a microbiome that could be compared with some
More cells
ecosystems.
than are the cells that belong to us, so to speak.
I never thought about it. That's one of these obvious ideas that someone thought before you and said, oh, come on, why didn't I think?
I just read that.
Simply we got the analogy the wrong way.
I just read that a few days ago, and there's something right about it. Ecosystems aren't typically selected, so you don't get this integration that is necessary for an organism to be an ecosystem that we can distinguish its boundaries, fairly clearly.
But one thing is that also there is an interesting argument by Frederic Bouchard that we are always talking about the fact that ecological systems are not selected, because we take we put a lot of emphasis on the reproduction component of fitness. But Frederic says, well, but fitness is also about persistence. So fitness has two components, persisting and reproducing. And ecosystem is very good at persisting. So he says, so there is a way we could talk about ecosystem selection in terms of persistence.
Yeah, well, I think that's right, but I think then we want to look at, and the way I would do it, as a philosopher, first of all, is to, that we're talking about persistence of what? Persistence is identity, essentially, through time. So what creates this identity through time?
Yeah.
That's basically what I've been arguing.
But I think there is something to investigate there, because if you take, for instance, multicellular organisms, you have levels of selection problems. So when the unicellular organisms, when they become multicellular, what happens is that the group selection becomes more important than the individual selection. And this generates the creation of a new unity at a higher level. So I think that's something that might have happened with organisms. Ecosystems were not selected at the group level, at the ecosystem level very strongly. When they got selected very strongly at the ecosystem level, this made a cohesive force that make them become organisms. We don't know if this might happen with forests.
Yeah, if you have an ecosystem that's too cohesive, it's an organism. That's quite possible.
And selection.
I kind of like that.
Selection could drive that. By paying off on individuation.
Over the long-term history of the Earth, there may be occasions where we get selection of ecosystems because of severe changes in global conditions, for example, temperature, rainfall, things like that. And a lot of ecosystems are going to die out, and other ones are going to survive. So maybe that's a case of selection of ecosystems, and it may well contribute to ecosystem functionality. To the best of my knowledge, this hasn't been looked at very much, but it's worth keeping in mind, that's for sure. Yeah, that's interesting.
Because I got here very,
Right.
very late, so I couldn't understand most of or part of you had said. My question is then a parallel question. If ecosystems, and I believe so, there is nothing to do with organisms, and we have discussed this afterwards, and I'm very convinced of that. Why then talk about ecosystem health? Isn't this inadequate to talk about the health of something that is not an organism? What do you think about it?
Bob Ulanowitz used the health term. I was quite happy with it in his writing, and I took it over from him. But the ecologists in general talk about resilience. So I've tried to translate Bob's work into talking about resilience instead of health. I'm not sure. There are different connotations.
And that's my question.
There's no question about it. There are different connotations. Right now there's a problem with pine beetles in the western part of the United States and Canada. They've started, they've killed so many pine trees that they're starting to feed on other trees. But this woman who's an expert in pine beetles thinks that things aren't really so bad, that they'll be self-limiting eventually. And the trees that survive will be the ones that aren't subject to pine beetle attack. She's seen this happen on a small scale, and she thinks it's going to happen on a large scale. There are other people who say, no, you're wrong. The forests are unhealthy. I mean, the trees are dying, you know? And this is at least partly due to changes in climate. Increased warmth is allowing the pine beetles to spread more widely than they had previously. And this is a serious ecological disaster on the way. It's hard to tell, you know, at a given time, which person is right. I'm more inclined to trust the person who's the expert on pine beetles myself, you know, just because she has this special expertise. And her arguments, when I've read them, have seem to be fairly strong. And independently of whether things are getting warmer and the pine beetles are spreading more, the effect that she's talking about some trees being able to resist them, and it's clear that some trees do resist them, then she may well be right. The pine beetles will eat out the ones that they can eat and kill, and then they won't have anything to eat, so they'll collapse. And this is part of the normal ecological cycle from her perspective. But the forest has become brittle because at the mature stage, its organization has required that it has basically a monoculture, and this makes it subtle, susceptible to things like the pine beetle, also forest fires. But pine beetle in particular is a case where, because some types of trees have been so successful at the mature stage, that the overhead has come down because there's not as much diversity. And consequently, it makes the system more brittle because there's not enough overhead for it to adjust. But what the pine beetle lady said, I wish I could remember her name, but what she's saying is that you have to look at the fact that the trees vary in their resistance to the pine beetle. And consequently, there's a certain amount of overhead built in that may not be obvious on the surface. That would be the way I would interpret it. And it seems to me that she may well be right. In the meantime, it's a disaster for the forest industry.
Well, I do think the notion of health is...
Sorry?
The notion of health is a complex analogy because
in
in medical science it's a very controversial concept for not being too clear. And I think it's the right ways to change for another metaphor like resilience. But resilience is also vague.
Yeah, well, that's what I'm trying to do here, is take Bob's notions and apply them to the idea of resilience.
And there is something very interesting here, because it's true that meta models like the resilience model should be vaguer than models, otherwise they wouldn't be meta models. But on the other hand, it looks a little too vague, particularly to say that a system is resilient when it changes but keeps their structure and function doesn't mean much if we're not clear about what's structure and what's function. And
yes,
this is being taken for granted.
Right.
Most of the people read this definition and feel very satisfied, but it's simply not clear enough unless you define these fundamental terms. And
yeah, the thing is that Bob's ethics can be used for actual management of systems like the Baltic Sea and Chesapeake Bay.
And Bob's
they're
approach is
successful
very
in
precise.
Chesapeake Bay in particular.
Bob's approach is very precise.
Yeah.
Unfortunately, as he's an engineer, I think ecologists have difficulty dealing with his ideas because he takes for an engineer perspective.
They are mathematically difficult, yeah.
But there is this book I gave you to read and told me it's not very satisfactory. It's a book on viability analysis.
Right.
It's 2011, so only 3 years from now, and they are trying to make resilience theory more precise, but mathematizing it, and they choose viability theory.
Right.
And I think all that you said is pointing to the direction of looking for another mathematical way of making resilience theory more precise by looking at descendants theory and information theory and not viability analysis. And I think this could be very, very, very promising if we could analyze mathematically the relation between organization, information, and resilience. This would be a way of making resilience clearer. In ascendance theory can be a way, and also thermodynamic depth, it can be a way because you can benefit from the wealth of knowledge on ecosystem ecology, on how to model ecosystem mathematically. And if we want to measure the amount of work needed to build an ecosystem, this is basically the amount of energy that is absorbed by the system, even though a complication is that we need to take into account dissipative process because...
Yeah, Kay and Schneider have paid particular attention to that. Unfortunately, James Kay died quite young, and Eric has never really carried out the project, and James was the brilliant person there behind it. He produced a coffee table book on the topic, though, with Dorian Sagan.
Okay, I think it's very promising, and I think we need to discuss this with Bob.
Anyway, it points the way for our next two papers.
Yeah.
Oh, I have a suggestion about the scheme that presented for water cycle. There is a book, a recent book, in electronic format that's called the Climate Future of Amazon, from a Brazilian researcher. And you have much more feedbacks between rain and forest than we can imagine.
Yeah, there's the same. There's the same. Interesting. There's the same effect in coastal Australia and in the west coast of Canada and northwest United States. And one of the things that, fortunately, the governments have realized that they can't allow really large-scale logging because it's going to disrupt the rain. And Sydney is already short of water, for example. And it gets its water from the mountains behind. They used to be covered by trees, but now not so much. But they're much more protected now than they were 10 years ago even. Yeah. Same thing will happen in the Amazon. It keeps getting cut down the way it is. Yeah.
I'll send you the link for the group. And I'm making some searches here. There is a paper by someone I never heard about, Johanna Hyman's, where she evaluates the effects of exploited ecosystems using information theory, and she combines ascendancy and resilience. I think there is something very promising.
Yeah. Yeah, I mean, one problem with this talk is I'm trying to draw things together as tightly as I can, but it's obvious that the talk raises more questions than it gives answers. And that's the state of the function in ecology. Has just become an issue that people have been concerned about in the last 10 years or so. Before that, people would ask, why worry about function? We don't want to worry about what's happening at the individual at the local level, interchanges between different species and like predator-prey relationships and things like that, all of which are important, but they all can be done within this overall model, which also gives you extensive variables that can be used to measure resilience or likely resilience, which is becoming more and more important for issues of ecosystem management. Not to mention understanding how ecosystems work. I didn't give very many examples of ecosystem function here. I have a lot more pictures that I used in a course that I gave here a couple of years ago. And I just didn't have time to present, and the talk was long enough as it was anyway. But there's a lot of good stuff in Alan and...
Excellent. Alan Excellent.
Yeah,
Lord
right.
Unified
Yeah,
Ecology.
yeah, brilliant book. Yeah.
Let me make a last question. In ecology, we are using all attributes of a species, putting them together, and then evaluating, for example, the amount of diversity in terms of these attributes.
Yeah,
And we don't care much about what are the specific functions that these attributes are related to, but we suppose that they have some function and they are affecting the role of the species. And I think that's the same for ecosystem. Because how can I call these all attributes without getting this problem of talking about what attributes when I don't know if functional ones?
Yeah, I see your point. Definitely, there's a lot of. I mean, for a long time, there's the organism or a group of organisms, a population, and this is population ecology basically. And then you have the relationship between the population and its ecology, where its ecology is external. And so it gets removed from the ecology in a weird way. This approach says, no, you shouldn't do that. But there's so much work that's been done in that area that obviously it's important to work. The more important thing to do is find ways, I think, to try to integrate it with a more extensive account of what's going on. It turns out that for the work in Chesapeake Bay and the Baltic Sea, a huge number of measurements. It took years to make the measurements. And there they were just using carbon as a stand-in. It turned out that there were certain cases where carbon wasn't the limiting factor. It was phosphorus, and in other cases nitrogen. So if you want to understand the flows, then you sometimes have to identify what the limiting factor is. And that's non-trivial in itself. But that requires study of the individual organisms and their relationship to other organisms. In other words, the organisms and their ecology. Where do they get their needs from? So that's not a minor role by any means in this approach. It's just that given this way of using the likelihood of the flows, putting them into a logarithmic form so you can add them together, it gives you a way to take the individual measurements and convert them into extensive measures to cover the whole system. But you still need the individual measurements. So there's no reason to throw out cost ecology. But the idea, I think I think a central idea is the idea of separating, it's just a mistake to separate the organism and the ecology. We do that with humans very easily, it's just natural. And I think that's a mistake that we have to somewhere or another get over. Maybe I should make that plea even stronger in my talk.
But I think part of what Ricardo says is because of the deep separation in ecology between ecosystem ecology and community ecology. So people understand composition, biodiversity, and the connection to energy, matter, and flows is very, very weak. And if we look at the biodiversity and ecosystem function research program, what they're trying to do in a way is this, trying to put together what we know about the diversity and composition of the species and the functions that are being played. But we can't understand the function unless we understand, from my point of view on function, what constraining action the species are doing, or the organisms, in fact, are doing with the flows of energy and matter. Otherwise, we can't understand the function.
Yeah, I think that's right. At the very least, you have to make measurements of the important constraining flows. But I'm sure that Bob would agree that's the least. That's just where you start. You're going to really understand what's going on. You're going to need to know a lot more about the behavioral interactions between various different species and within particular species in order to understand how they fit into the ecosystem and whether or not they contribute and in what respects they contribute to the overall resilience of the ecosystem. So there's a lot more likely going on than this relatively simple model shows. But like I say, the first attempt was particularly phenomenological, and they just measured carbon exchange. Now they're finding, no, there are other limiting factors, so they're looking at other types of exchange. But why not behavioral exchange? That becomes important too. Sometimes you can use carbon exchange as a substitute for behavioral exchange if you think that mostly what species do is eat. But elephants don't just eat, they trample forests, and that's important to the ecology of places where you find elephants.
Okay. Thank you, John, again.
Oh, thank you.
Good.